Assalamualaikum and greetings everyone. Let's continue our lecture on the last chapter entitled Heat Loss in Tin Fin. So, what is fin? Fin is an extended surface added onto a surface of a structure to enhance the rate of heat transfer from the structure. For example, in this motorcycle engine block. In this course, we will focus on thin rectangular fin that usually used in heat sink design for microelectronic cooling system. Therefore, in this course, we will develop finite element formulation to model and analyze the heat transfer process in thin rectangular fins. The objective of our analysis is to determine the temperature distribution in the fin and the total heat dissipated. To simplify the heat transfer in thin fins, the temperature gradient is assumed to be exist in one direction only. Thus, the heat transfer through thin fin can be treated as one-dimensional. Heat flows through the fin by the conduction, as shown in this figure, and dissipated to the ambient by the convection process. Therefore, in this topic, two heat transfer modes occur simultaneously. When the heat flows from the fin base towards the fin tip, the energy balance is given by this equation 1, where Q represents the internal heat generation. And in general, the thermal conductivity K varies along the x direction. However, for isotropic and homogeneous material, K is uniform and has the same value in all directions. For example, homogeneous material is like aluminium, steel, titanium, or any metallic materials. For the purpose of finite element modeling, since the heat transfer through thin fin is assumed one-dimensional, we will model the fin using 1D heat transfer elements. For example, the fin is discretized into 3 elements with n equal length as shown below. So in this case, we only consider the thin structure to be modeled in our finite element modeling. So in this case, we will be going to divide the length of this fin into 3 segments or 3 elements. Therefore, we have to create 4 nodes as shown in this slide. And of course, the T1 usually is equal to the temperature of the fin base. If we create 3 elements, meaning that we're going to have 3 unknowns. If we create 2 elements, meaning that we're going to have 2 unknowns. Therefore, the unknowns, it depends on the number of elements. Once we have defined or determined the temperature at the nodes, then we can predict the temperature at any point between the 2 nodes. In order to determine the temperature at any point between 2 nodes, we need to establish the temperature function. Similarly, like in the previous chapter, we're going to assume the temperature varies linearly within the element. Therefore, the linear temperature function can be expressed as follows, which is exactly like in the previous chapter. And we can simplify this equation as shown. The temperature is equal to N1 T1 plus N2 T2, where N1 and N2 is called the shape function. Since 1D heat transfer element is used to model the thin fins, which is similar to the element used to model the plane wall in the previous chapter, therefore, we can assume the element conductivity metric of the thin fin is equal to the element conductivity metric of the plane wall, as shown in the equation 4, where K is the thermal conductivity of the film material and L is the element length. As mentioned in the second slide of this chapter, two heat transfer modes, which is conduction and convection, occur simultaneously. Therefore, to include the effect of convection heat transfer, we need also to establish a convection heat transfer matrix as shown in equation 5, where H is the convective heat transfer coefficient with the unit watt per meter square Kelvin or watt per meter square Celsius. L is the element length and T is the thickness of the fin. So far, we have defined the K matrix as well as the H matrix for the thin fin. Let's have a look on our first example. In this example, a rectangular aluminum fin is used to remove heat from a surface whose temperature is 80 degrees Celsius as shown in this figure. And the temperature of the ambient air is 25 degrees Celsius with convection heat transfer coefficient of 120 watt per meter square Kelvin. The thermal conductivity of aluminium is 168 watt per meter Kelvin. The fin is 120 mm long as shown in this figure, 200 mm wide and 1 mm thick as shown in this figure. The tip and the fin side surfaces are assumed to be insulated, while the top and the bottom surfaces are exposed to the convective environment. Let's determine the conductivity matrix as well as the heat transfer matrix due to convection. Now, let's try to solve this problem by using three heat transfer elements. And to simplify our calculation later on, it is better to model all the elements with n equal length as shown in this free body diagram. It shows that all the elements is having the same length, which is 40 mm. Besides that, for thin film problems, in general, the T1 or the temperature of node 1 is always assumed to be the same as the fin base temperature or the body temperature. Therefore, in this example, there are only 3 degrees of freedom as shown, which is temperature at node 2, node 3, and node 4. Okay, now let's determine the element conductivity matrix for each element by using this equation. Please take note that as the fin is made from a homogeneous material, therefore, the conductivity coefficient for all elements will be constant or will be the same. Similarly, for the length, as we model the element with equal length, therefore, the length of the element is constant for all the elements. Therefore, the K matrix for each element will be the same as shown. Then, in order to obtain the global conductivity matrix, we just need to assemble all these three elements K matrix into one global matrix as shown here, where the first part of this global matrix is taken from element 1 as it corresponds to T1 and T2. The middle part of this K matrix is taken from element 2 as it corresponds to T2 and T3. And the last part here is correspond to element 3 as it corresponds to T3 and T4. At every intercept, of course, we had to take the summation between the two matrices. Now, let's determine the convection heat transfer matrix for each element by using this equation. Similarly, since all elements have the same length and thickness, as well as all the elements has been exposed to the same convective environment, therefore, the convection heat transfer matrix for all elements will be the same as shown in this slide, where the H matrix 1 equal to H2 equal to H3. Once we have determined the conventional heat transfer matrix for all elements, then we can determine the global H matrix as shown in this slide, where the first part of this H global matrix is taken from element 1 as it corresponds to T1 and T2. The middle part is taken from element 2 as it corresponds to T2 and T3, and the last one, this part, is taken from element 3 as it corresponds to the unknown T3 and T4. Similarly, at any intercept, we just need to take the summation between the two matrices. Beside the K matrix and the H matrix, the third important parameters required for set up the system linear equation in a thin film problem is called the element heat rate vector. In thin films, the heat rate vector is contributed also by the convention heat loss from the fins. By using the Galerkin approach, the element heat rate vector can be expressed as shown in equation 6, where the T infinity is ambient temperature and the rest parameters has been defined in the previous slides. After we have determined the element conductivity matrix, the element convention heat transfer matrix, and the element heat rate vector, then we can set up the system linear equation as shown in equation 7 for a single element, or in equation 8 if we have more than one element. Please take note that if the fin is insulated, then the magnitude, the convention heat transfer matrix, and the heat rate vector will be 0. Okay, now let's reconsider the example 1. And in this example, we would like to assemble the global heat rate vector for the fin and to write the global system of linear equation for this problem. In order to obtain the global heat rate vector for this problem, first we have to determine the heat rate vector for each element by using this equation. Similarly, since all elements have the same length and thickness, as well as has been exposed to the same convective environment, therefore, the heat rate vector for all elements will be the same, as shown in this slide. Once we have determined the heat rate vector for each element, then only we can assemble it to obtain the global heat rate vector as shown in this slide, where these terms are taken from the first element as it corresponds to T1 and T2, and next this term are taken from the second element as it corresponds to T2 and T3, and the last one, this term are taken from the third element as it corresponds to T3 and T4. At any intercepts between the two matrices, we just need to get the summation. In this example, as we use more than one element, therefore, we are going to set up the global system of linear equation using the equation shown. All the products like the global conductivity matrix, the global convention heat transfer matrix, as well as the global heat rate vector have been determined in the previous slides as shown. The next step, you just need to get the summation of matrix K plus H as shown in this equation. To solve this, we just need to add the matrix K and H according to their position. For example, the K11 we need to add with H11. For K12, we need to add with H12. While for K21, we need to add with H to 1. And similarly, for K to 2, we need to add with H to 2. And so on for other values. By doing so, we can obtain the product K plus H as shown. Next, we just need to add the unknown temperature matrix and the global heat rate vector on the right side. However, at this point, this system linear equation have no solution. We have to impose the boundary condition at the first place before we can solve the unknown temperature. Then we're going to discuss about the boundary condition in the next slide. In thin film problems, there are two thermal boundary conditions. The first one, temperature at the base of the fin, Tb, is assumed to be the same as the temperature of the structure. As mentioned in the previous slide, number 11. The second boundary condition, the tip of the fin can be assumed as adiabatic or insulated. Therefore, the heat flux is equal to 0. Hence, the boundary conditions for the fin are the Tb is equal to T1 at x equal to 0, meaning that the temperature at the beginning of the fin is specified. The second one, the heat flux is equal to 0 at x equal to L, or at the tip of the fin, meaning that the heat flux at the tip of the fin is specified. However, the second boundary condition, when we add it into our system linear equation, give no difference, as the value is 0. Okay, now let's reconsider the previous example. So in this example, we're going to apply the boundary conditions and to solve the unknown temperature distribution in the fin. In previous example, we have determined the global system linear equation for this problem without any boundary conditions. Now, let's impose the boundary condition. In this example, actually, there are two boundary conditions. The first one is the heat flux at the tip of the fin as well as at its side surfaces are 0, as we assume those areas are to be insulated. Nevertheless, when we apply these boundary conditions in our global system linear equation, it won't give any differences, as the heat flux is equal to 0. Therefore, we can neglect this boundary condition and only focus on the second boundary condition, which is the specified temperature. As mentioned previously, in thin fins problem, the temperature at node 1 in general is assumed to be the same as the temperature at the fin base. So, in this problem, T1 is already specified. Therefore, we can eliminate the row and column for T1, as it is no more useful to our global system linear equation, as the unknown that correspond to row and column number 1 is already specified. However, we still have to check the value in column 1 at other rows. For example, at rows number 2, the value in column 1 is non-zero, as shown here. If this value we multiply with 353, it will give a constant value, and we cannot neglect this value. We have to bring this constant value to the right side as shown. For row number 3 and number 4, it has no changes as the values in column 1 at row number 3 and row number 4 are 0. Okay, for those who are still unclear, I will show you why we have to do this. Let's take out equation 2 from this matrix, which is the equation from row number 2. We bring outside. We will have negative 2.6 kilo times 353 plus 14.8 kilo times T2 minus 2.6 kilo T3 equal 2860.8 times 10 power 3 or kilo. We can see clearly there is a constant value on the left side of this equation on the first term. In common practice, we have to bring this constant value to the other side on the left. That is what we are trying to do in the above modifications. So we have negative value on the left side. When we bring to the right side, it will become positive. That's why this value is positive. Next, we just need to consider those values in the green box for our final step to determine the unknown nodal temperature. So, once we have modified our system linear equation after impose all the boundary conditions as shown here, the next step we just need to use the calculator to calculate the unknown nodal temperature as shown. As mentioned before, our second objective in this topic is to determine the total heat dissipated from the fin. Therefore, the heat dissipated from a single element can be estimated using the Newton's law of cooling, as shown in equation 8, that will give the heat dissipated in unit watt. In order to determine the total heat dissipated from the fin, we just need to get the summation of the heat dissipated from all elements as shown in equation 9. Now, let's reconsider the previous example. As we already determined the temperature distribution in this problem, now we would like to estimate the total amount of heat dissipated from the fin to the ambient air. Previously, we have determined the temperature distribution for this thin fin as shown. By using this information, we can calculate the heat loss from each element by using this equation. For element 1, we just need to replace the small h with 120, as this value is taken from the information given. And then multiply with the T average. In this case, the T average is taken from the average of the temperature in element 1, which is between T1 and T2, minus the ambient temperature, which is also taken from the information given. There is the value 25 degrees Celsius. And of course, in this case, we have converted it into Kelvin unit. And then we multiply this equation with the surface area of element 1 that exposed to the convection process. As we calculate the surface area of element 1, then please remember to consider only the length of element 1, not the length of the fin. So meaning that in this case, we are calculate this area. The length will be 40 millimeter and the width will be 200 millimeter, which is constant for all elements, and we calculate this area. That's why we have 0.04 multiplied with 0.2. And of course, we multiply by 2, in this case, in order to consider the top and the bottom surfaces of element 1 that exposed to the same convection process. For element 2, H is constant, T ambient is constant, the surface area is also constant as we discretize the thin fin with an equal length. Therefore, the surface area for element 1, element 2 and element 3 will be the same. For element 3, everything is similar except for the average temperature, where the average temperature for element 3 is taken from element 3, which is between T3 and T4. For element 2, the T average is between T2 and T3. Besides that, please take note that in this calculation, we do not consider the side surfaces of the fin as well as the tip surface of the fin, because in this example, those areas are assumed to be insulated. Therefore, there will be no heat loss. Once we have determined the heat loss from each element, then we can calculate the total heat loss from the fin by calculating the summation of the heat loss from all elements, as shown in this slide. Okay, please watch the part 2 of this topic for the other examples.